This is the first lecture in our unit on solutions. This first lecture is an introduction to solutions. And when we talk about a solution in the chemistry sense, what we're talking about is a homogeneous mixture, and that is two or more substances that are not chemically bonded together. Some parts of the solution you need to be familiar with are two terms called the solvent and the solute. The solvent is the substance that does the dissolving. So typically that's going to be water or alcohol or something like ethanol. And the solute is what is dissolved in the solvent. So if you had, for example, salt water, water is the solvent and salt is the solute. And if you have a solution that is based on water, that is called an aqueous solution, and that is very common in chemistry. When you have an aqueous solution and you're writing a formula for it, you would usually denote that with a little subscript that has AQ. Usually people think of a solution as being a liquid where something has been dissolved into it, but a solution could actually be a gas or a solid as well. Here are some examples of different types of solutions. What they all have in common is that they are all homogeneous mixtures, meaning that you cannot see the different parts in the mixture. So for example, an alloy such as steel would be a solid-solid solution where the different components of the steel are all mixed together and you can't see the different parts of it. So when we talk about dissolving, we need to look at what does that mean in the chemical scientific sense. Another term for dissolving is dissolution. And basically to dissolve is when you have a polar solvent that pulls apart a polar solute, or vice versa with a non-polar solvent and a non-polar solute. So what that means is that the solvent is going to be attracted to the solute molecules and is going to separate the solute molecules from each other. So when this happens, there's going to be a break in intermolecular forces. So for example, if you had a substance that's held together by hydrogen bonds, the solvent is going to break apart the hydrogen bonds in order to pull the different solute particles apart. But the key thing is that the intermolecular forces are broken, however the covalent bonds are not affected. So if you have sugar dissolving in water, the different glucose molecules in your sugar sample are going to break apart from each other. However, the glucose is going to remain intact, meaning that the carbon, hydrogen, and oxygen are still going to be bonded to each other. So because when we look at dissolving, we have polar solvent goes with a polar solute, or a nonpolar solvent goes with a nonpolar solute. We use this term like dissolves like to help us remember that. Another example of dissolving is ethanol in water. Ethanol is typically a liquid dissolving in liquid water. Here would be, if you pour some ethanol into water, there would be a sort of a puddle of ethanol in which there is hydrogen bonding in this case that is keeping all the ethanol molecules together. However, when the water molecules come in contact with the ethanol molecules, the intermolecular force or attraction between the water and the ethanol is going to be greater than the force that is keeping the ethanol together. So as we can see in this picture, the water molecules are going to be pulling the ethanol molecules apart, and ethanol and water are going to be attracted to each other. So ethanol will dissolve in the water. So every solute we've referred to so far has been covalent. Dissociation is a particular type of dissolving that applies to ionic substances. And this is a different process because what we'll have is we do have a breaking of the bonds. And in this case, the ions are broken. So dissociation basically means that ions are separated. So you would have a molecule and you separate it into individual ions. And this is what happens when a ionic substance is dissolved, so we give it a special name. This is an example of dissociation. If you dropped a salt crystal into water, the salt crystal would be made of many ionic bonds between here sodium and chlorine. Here's another sodium and chlorine. And then there's the electrostatic attraction that is between the individual molecules. So what happens is that water molecules, because they are polar, are going to be attracted to the positive and the negative ions that are in the crystal. So in this picture we can see that the positive pole of the water molecule, if we drew here's the dipole moment arrow, so this would be the positive end, and it's attracted to the negative ion. If we look at the positive ion, the sodium ion here, we see that we have the opposite case, where we have the negative pole of the water molecules are attracted. So this would happen to this entire crystal. The ions would be torn apart one by one, and that is what happens when you have salt dissolving. And again, because we are breaking bonds in this case, we give this a special term, and this is called dissociation. Let's look at an animation of this. In this animation from Northland College, we see salt being poured into water. Water again is the solvent. Salt is the solute. And if we look at this on a microscopic level, we can again see that the polar molecules, the polar water, are going to be attracted to the different ions within the salt. And so each ion gets pulled apart from each other. If you're wondering why the ions do not go back together, you can see that in this picture here they're showing what's called a hydration shell. And what that is basically the individual ions are going to be buffered from each other because they're going to be completely surrounded by the water molecules. So why do some substances dissolve and others do not? First of all, like we said, you have to look at like dissolves like. So you have to look at the polarity of the solute and the polarity of the solvent. But then once you have looked at that, you also have to look at the intermolecular forces. If the attractive force between the solvent and the solute is stronger than the force that is holding the solute together, then the substance will dissolve or dissociate. We would then consider that substance to be soluble. For example, salt will dissociate in water, so we consider salt to be water soluble. Salt is not soluble in oil, and mainly that is because oil is nonpolar and salt is ionic, so there is no attractive force between them. However, if you have a substance that is weaker, where the force is weaker between the solute and solvent than the force between the solute molecules, so the force holding them together, the substance will not dissolve or dissociate, and we would then call that substance insoluble. So another way of saying insoluble is immiscible, which just basically describes if you have two substances that will not mix with each other, they are immiscible, or one is insoluble in the other. So salt is insoluble or immiscible in oil. Let's take a closer look at oil and water. Here we can see that oil floats on top of a sample of water. That is because oil is less dense than water, but also because oil is a nonpolar molecule. So it's difficult to tell in this picture, but what they're showing you is that this is one long hydrocarbon. This is a very long fatty acid tail. It is not many individual molecules. Oil molecules are very, 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 very long, so they're just showing one here. Here we can see the individual water molecules, and we can see the hydrogen bond that is between the molecules holding them together. We know that that water molecules are polar and oil molecules are nonpolar. So because of the like dissolves like rule, these two will not dissolve in each other. So oil is immiscible in water. Some other important terms to know which are not specific to solutions, but they are related to miscibility, are hydrophobic and hydrophilic. A substance that is hydrophobic is afraid of water. So phobia, like arachnophobia, is the fear of spiders. Hydrophobia is the fear of water. So oil is hydrophobic, and what that means is that basically oil will not mix with water, as we already know. So if you were to take a sample of water and oil and cap it and shake it up, eventually what would happen is that there would be little bubbles that would form, they would clump together, and it would go right back to the same layering process that it was before. So hydrophobic means any substance that will not mix with water. The opposite of hydrophobic is hydrophilic. Philia means love, so a substance that will dissolve in water is hydrophilic. And we had looked at ethanol in water earlier, and if we were to look at those in a test tube, we would see that ethanol in water looks very similar to just a pure sample of water. There is not a layer. If we were looking at oil in water again, we would see that layer of oil floating on top of the layer of water. So oil is hydrophilic. Oftentimes in pharmaceutical chemistry or in cooking, there would be a desire to mix something that is polar and non-polar, such as oil and vinegar if you're making a salad dressing, or different types of oil moisturizers with water in that would be commonly seen in lotion or in shampoo. So you would use what's called an emulsifier. An emulsifier is a substance that basically has a polar part and a non-polar part, and because of those two different parts, it can sort of bridge the gap between the solvent and the solute, keeping them together. So this is a molecule you can see of what's called lecithin, and in this molecule there are 3 branches off of the main carbon here. There's a very long lipid tail, there's 2 of them, and we know lipids are nonpolar. And then there is a phosphate and nitrogen group, and this is the polar section, because we could look at the electronegativity values and we would see that there's positive and negatives. So if you were to put this lecithin molecule in this dressing here, we see there's an oil layer and a vinegar layer. Then this lecithin molecule, the lipid part, is going to bond with or dissolve in the oil, and the polar section of lecithin is going to bond with or be dissolved into the vinegar. Then when you were to shake it, then you'll be able to keep this solution, you could keep it emulsified, which means mixed together, because the individual oil and vinegar molecules are now going to be able to be close to each other rather than separating into groups. So if you were to go home and look at almost anything in any kind of sauce in your refrigerator, or almost any kind of cream or liquid type substance that you have in your cabinet, you're going to see that there is some sort of emulsifier in that. A similar type molecule to an emulsifier is a detergent. A detergent is a similar molecule because it also has a polar and a non-polar portion, and detergents are more used for cleaning. So for example, SLS, or sodium lauryl sulfate, is often found in cleaning solutions, in soap, in shampoo, in body wash, and it again has a very long fatty acid tail, and it is the non-polar portion, and the front portion is very polar. So if you were to have a clump of dirt, when you wash your hands, for example, and you have dirt on your hands, these many sodium lauryl sulfate molecules are going to surround that clump of dirt. Dirt often has oil in it, and oil from your hands and oil from grease, and so the fatty acid non-polar tails of these molecules are going to be attracted to and are going to clump around little individual bits of dirt. Then the outside head, or the polar ends, are going to be able to dissolve in water. So when you wash your hands, the dirt is going to sort of like get clumped and trapped in a little ball, and the ball will then just wash down the drain because it will dissolve in the water. So detergents are very similar to emulsifiers, but they sort of serve a different purpose. MSNBC has a very interesting segment on the oil spill in the Gulf of Mexico, and what they look at is what's called a dispersant, which is basically a detergent. And they wanted to follow some scientists who are looking for a special kind of detergent that can be used on the in the ocean, and they want to figure out a way that they can use one that is safe for the environment and that can be used to clean up the environment. So at this website, this is a very interesting bit of chemistry. It's called Chemistry Now, and it's a bit of interesting chemistry that's in the news about, and it has a very good description of emulsifiers and detergents and how detergents were used in the cleanup efforts. To finish this lecture, I've provided you with 3 practice problems. I recommend looking through these practice problems and going back through the lecture to find out what the answers are, to think about what the answers would be, or to maybe look them up online, so to sort of test your understanding of what we've gone through in the lecture today.